How's it going? Hope y'all are doing well today. Okay. Alright, last time we wrapped up 7.3 and we also talked about section 7.4. Were there any questions on any of that homework that I assigned? Oh, today is Tuesday, so number 9 for 7.4. Okay. So, one, you may be in the wrong class today. You may be supposed to be in the other class. Because I think our class is Monday, Wednesday at 11, and this is Tuesday, Thursday. Yeah, sorry, that's okay. Mrs. Nice is probably expecting you. I think she sent an email already for. Yeah, you too. Alright, yeah, let's look at number 9 on page 74. So we had y equals 2/3 x to the 3/2 plus 1. This is page 481. And if we look at the graph that they give us, it's a curve that starts at 1 on the y-axis and kind of goes up from there. but specifically they want us to stop, it looks like, at x equals 1. Okay, so first thing on this problem is we can tell just from this graph, if this is the part of the graph that they want us to focus on, and you can see in the book it's shaded in, then we'll just go from x equals 0 to x equals 1, and that'll be our limits of integration. Alright, now we know that the formula is L equals integral a to b square root of 1 plus f prime of x squared, and then dx. So, in this case, this is our f of x, or y, as it is, so we need to find y prime. Now, this is just a power rule, basically, that we're looking at. So we take 3/2, the exponent, multiply it times 2/3, and then we subtract 1 from the exponent, so 3/2 minus 1 is 1/2, and then derivative of 1 is just 0. And so what we find is that when we simplify this, the 2's and the 3's cancel out, so y prime is just x to the 1/2, which is the square root of x. Now, we go ahead and plug that in here for f prime of x, and we have to square that, which is actually nice, because we have a square root here. Once we square that, that'll change it into a regular x. So we integrate 0 to 1, as we said. And we have 1 plus x under the square root, and then dx. Okay. Now, looking at this, it's not too bad. In fact, we could go ahead and do a u substitution here. We can let u equal this 1 plus x, which is great because its derivative is just 1, so we can just say du replaces dx straight up, and then from there, L, we'll just have the square root of u du. Now, we still want to make sure we carry out all the steps in proper detail. Square root of u, again, helps to make that u to the 1/2 power to integrate. And so the integral of u to the 1/2 is u to the 3/2 divided by 3/2 which that would be 2/3. Replace u with 1 plus x, and then raise it to the 3/2 power from 0 to 1. Okay, and so that completes the integration. Now our last step is to just plug in our limits and see what we have. If we plug in x equals 1, 1 plus 1 gives us 2 to the 3/2 power. If we plug in 0, we get 1 plus 0, which is 1 to the 3/2 power. And we, of course, subtract those two values. From here, we can't really do a whole lot to simplify this. We could write it like this if we like. Or, if we wanted to, we could actually go ahead and approximate it. But this is actually fine here. 2 to the 3/2 is the same as 2 root 2. And then 1 to the 3/2 is just 1. So I think that's the acceptable answer here. But if you wanted to go ahead and approximate it, that would be fine also. Does that help? Yasmin? Were there other questions on homework? Okay. All right. So today we're going to continue looking at chapter 7. Now, we just looked at the first half of 7.4 last time, so I think what we'll do today is we'll finish 7.4, and then we'll go on to 7.5 as well. Hopefully, I think that should take all of today's class, the rest of that section. We're looking at Thursday doing 7.6, and then that wraps up our material for chapter 7. So I would say next week we'll have a test, and probably what I'll do is on Tuesday we can what do I want to do here? Probably Tuesday we can have a day to go over questions, and any questions anyone has. I'll give you a list of review problems coming this Thursday so you can work on those, something like that, and then on you can work on those next Tuesday in class, and then I'll give you until the following Tuesday basically to take the exam, probably till Monday night at midnight or something. So if you wanted to take the exam Thursday or during class next week, then you could certainly do that. And it'll be in Canvas, the exam. And what you should expect to need to do is to you'll submit your answer by posting an image of your work. And let me know if anyone is going to have difficulty doing that. Anyway, so that's kind of what we're talking about there. And you'll have a window of about a week to work on it, so that'll be good. But, I mean, that's the window you have available, so anytime during that week you'll be able to take it, but you'll only have that block of time to actually complete the test, which will be like 2 or 3 hours. So anyway, I talked about making some of it take home. Not completely sold on that, but one problem in particular I think I will make a take home problem, because it's just so much longer than the rest of the problems, and we'll see why when we go over it on this Thursday. Yeah. Uh, I still haven't posted the calendar yet, but as you can see, we do have a test coming up Thursday, which will be the 17th. So that'll be our first test. All right. So let's talk about this other half of section 7.4 today, which is on the area of a surface of revolution. Okay. Um, when we talk about the area of a surface of revolution, that means we want the surface area of the object that's been revolved. It actually only gets the lateral area around the sides. It doesn't get like the top or the bottom, but just the side area is what we're talking about. So like if we had a cylindrical can, for instance, then the area around that on the sides, the vertical facing sides, that's what we would be finding here, and that would be the area of the surface of revolution, which in the case of a cylinder would just be the circumference times the height, much like a cylindrical shell. And actually, you'll see that the formula is very similar to that of a cylindrical shell. But the idea, let me show you a concept. Maybe we have this curve. We call this f of x, but it's being revolved around this vertical axis. And so the idea is that, okay, we're going to make this go around the axis here and create kind of a bowl-shaped object. Okay. So with this bowl-shaped object, we want the area of the outside. We don't want the top, we don't want the bottom. Now the bottom is just a single point anyway. So not a great bowl because it doesn't have a lot of stability. But that's kind of the general shape that we're working with. But we just want the area of that outside portion of the bowl, not the top or bottom. Now in this case, it actually represents the material being used, like the area of the material being used. In the case of a bowl specifically, we'd have to include the thickness of the material, of the glass or the ceramic or whatever. Yeah, or even plastic. Could be a plastic bowl. Especially if it comes to a single point like this, I would hope it's plastic, because like I said, not a lot of stability in this design. Anyway, the concept is that we basically have this arc length that is being revolved around this vertical axis. And so when we think of this, it's kind of like a cylindrical shell, like I said, but it involves an arc length instead. So when we look at the formula for this, this is A to B. When we look at the formula, it'll have shades of both of those formulas. So now this is not volume anymore, this is area. So it'll be 2 pi integral A to B of r of x times the square root of 1 plus f prime of x squared dx. So we keep our radius function, which in this case is just our x value. This is just like with the shell method, because if our function is right here, then how far we are away from the axis of revolution is just whatever the x value is. That's the horizontal component here. Okay, so r of x is equal to x. F of x is whatever it is, and then we'll take its derivative and plug it into this function. And from there, we'll just solve the problem. Okay, so if we're going around the y-axis, then r of x is always just going to be x, and then we use our function here, and then we apply our limits as well. So that's our formula for the area of revolution. I'm probably not even going to, probably won't include a test problem on this, but I'd like to go over it at least. Alright, so let's look at an application here. Now, actually, before we do that, before we dive into that, the alternative is if we take this figure, and again we have a function, f of x. What if we go around the x-axis instead of the y-axis? Well, in this case, the radius, r of x, is now the vertical component, because this is how far we are from the axis vertically, rather than the axis being here. It's now here. So now we have our vertical component. So our area in this scenario is actually f of x square root of 1 plus f prime of x squared dx. And the reasoning here is that f of x is basically the same as r of x. Here r of x was just x, but in this case the radius is now whatever f of x represents, whatever values we get there. That's from A to B. Okay. And we still include the arc length as well. So, depending on our scenario, we have one or the other set up. This one creates kind of a horn shape, I guess. Okay, so that's our two formulas. It really just depends which way we're going, how we end up applying it. Okay, so I want to look at number 40 on page 482. Now, in number 40, we have y equals 2 square root of x. And it's going about the x-axis. Which, yeah, there we go. Now, the book actually provides a graph for this, because we don't actually want the whole thing, because, you know, you think of the graph for y equals 2 square root of x, this is kind of half parabola that goes up and over to the right from the origin. Now the book only wants a specific part of that, which appears to go from 4 to 9. Okay. And you can see the graph here in the textbook. We can see that, here's our function y equals 2 square root of x, and it's going to create this shape when it's revolved. It's kind of nice to see the shape reference. But yeah, we're going around the x-axis, and this is our formula of y equals 2 square root of x right here. All right. So, since we're going around the x-axis, you use this formula, 2 pi integral a to b of f of x square root of 1 plus f prime of x squared dx. So now, let's go ahead and find f prime of x and square it so we can plug it into the formula there. Now f of x, since we have 2 root x, we could say that's 2x to the 1/2, just for simplicity's sake. What would be the derivative of 2x to the 1/2? Does anyone have that? Okay. We're multiplying by 1/2 in front, so 1/2 times 2 is just 1. And then we decrease the exponent by 1, so we'll have x to the negative 1/2. So that's f prime of x. So if we want to, we can change that back now into a square root instead of an exponent. So we can make that 1 over the square root of x. Because the negative means it's going to drop down to the denominator, and 1/2 powers means it's still a square root. Yeah, 1 over square root of x. Sorry, I just saw that. Okay. So we'll take 2 square root of x, plug that in for f of x, and we'll take 1 over root x, plug that in for f prime. And like I said, it looks like it goes from 4 to 9, so that's what I'm going to use. It's kind of hard to tell on the picture here whether that's dropped to 8 or 9. And I went ahead and chose 9. Actually, no, 8 might be better, but it looks like 9. This is where this dot is. I'm going to go with 9. Because we're working with square roots, 9 feels like it might be a better number anyway than 8, because at least 9 is a perfect square. I'm not sure if it works out in a way that allows us to exploit that, but anyway. So we have 2 square root of x, that's f of x, and then we have square root of 1 plus, and then f prime of x squared, and then dx. Left a lot of room there for some reason. Okay. So, first of all, we would go through and let's make sure we square what's under the radical, or sorry, in here first. That's 1 plus 1 over x dx. But now, here's where the properties of square roots are important. We have the square root of x here, and we have the square root of 1 plus 1 over x. We can actually take, because they're both under square roots, we can kind of put them together into a single square root. And so what we end up with is x times 1 plus 1 over x. And so the idea is that a product of square roots is equivalent to the square root of that product. So with these two terms being separate, we can combine them into a single radical, as long as it's the same radical, both square roots. And we can distribute the x now to both of these terms. Okay. So, if we do that, we end up with x times 1 is x, and x times 1 over x is 1. So we actually get a relatively nice expression under the radical that we can work with as far as using just a simple u substitution to continue. This x plus 1, though, it'd almost be better if we had 3 and 8 here rather than 4 and 9, just because we're going to add 1 to everything and then take the square root. But anyway, there's no way I could look at that graph and try to sell it as 3 and 8. It looks like 4 and 9 for sure. So we know we can do a u equals x plus 1 substitution. Du then is just 1 times dx. So pretty straightforward substitution there. And then we have 2u to the 1/2, or because it's the square root of u, and then du. Alright, now what is the integral of 2u to the 1/2? Four u to the 3/2? Close. Very close. No, it's definitely u to the 3/2, and there's definitely a 4 there, but there's one other thing in the denominator. Four thirds. Yeah. So what happens is we add 1 here, so it'd be u to the 3/2. I think everyone was on board with that. But then we divide by 3/2. Now, and then we still had another 2 in front of that. And so by dividing by 3/2, we actually end up multiplying by 2/3. So 2 times 2 over 3 gives us the 4/3 u to the 3/2. Right, we'd use the reciprocal. Unfortunately, there's a lot of ways we could mess that up, so we have to be very careful here. Details like this, while they seem insignificant, but it does affect our overall answer at the end, so we want to be sure we're able to get the right answer ultimately. Alright, now the 4/3 I'm just going to factor out. That's why I left room there. And we could even just make that at 8 pi over 3 if we want. And u is once again x plus 1, as we said, to the 3 halves power. And that's from 4 to 9. And so this will be 8 pi over 3. If we plug in 9, we get 10 to the 3 halves power. If we plug in 4, we get 5 to the 3 halves power. And really, that's all that we can do. We're not going to be able to simplify that, unfortunately. It seems like we might, because we have like 10 and 5 here, because we feel like there's some commonality. But it turns out we can't. We can't do anything with those. The only thing we could do at this point is approximate. I mean, we could write it as 10 root 10 minus 5 root 5, but we still can't combine those things no matter what we do. So we could still approximate the answer. That's about all we have left as an option. So if we approximate the answer, 10 square root 10 minus 5 square root 5. Okay. And that gives us an answer, and then we multiply that by 8 pi and then divide by 3. So we get about 171.3 square units. You know, whether we're looking at centimeters squared or inches squared or feet squared, meters, whatever it is we're talking about. It is an area measure, so it's in squares, whatever the measurement is. Okay. Right, so I mean that's our surface area, and like I said, not going to really test on that, but I wanted to talk about it at least so we can go over the concept. Let's see, and I think that takes care of what we're going to talk about in that particular section. Yeah. Okay. So we move on to section 7.5, which is on work. Now, when we talk about work, we're going back to physics. I don't know how many of you have had physics or are currently in physics. Probably some of you are in Physics 1 right now, since you need Cal 1 as a prerequisite to that. Anyway, may or may not be something you've talked about there just yet. But the concept of work is if we apply a force to an object over a distance, this is the amount of work done. So we're looking at work done by applying a force to an object, I guess we could say, from, let's say, from point A to point B. Now, so when we talk about work done, there's different units that we use depending on which system we're in. If we're in metric, what's our typical unit for work? Is anyone familiar with that? So in metric, our units of measurement for force can be in joules or Newton meters, for instance, which technically is the same thing as a joule, Newton meters. One joule is 1 Newton meter. But it's a lot easier to say joules rather than Newton meters. Anyway, when we say Newton dash meters, that means they're actually the newtons, the force, is multiplied by the distance meters. So when they're multiplied together rather than divided, it's not newtons per meter, it's actually newtons and meters together. So we kind of hyphenate it in that scenario. In imperial units, we would use foot pounds or feet pounds. And we can adjust from there. Like, we could actually use Newton kilometers if needed, or kilonewton meters, or whatever relative size is appropriate here. We tend to kind of our basic measurement is Newton meters or foot pounds in the two different systems, just because those are our basic units. Newtons for force, meters for distance, and then potentially, well, no, that's just it right there. And in imperial, it would be feet and pounds. That's kind of our basic units there. Anyway, now, when we say work done by applying a force, the force could be a constant force or it could be a variable force. Okay, so if we look at work done by a constant force, which we're not particularly interested in here, but work done by a constant force is typically written as, we'll use W for work, which is force times distance. Okay. Now, force kind of depends on the angle. Like, if we're just pushing an object and it's frictionless, let's say, then F is just the force that we use to apply. But if we're pushing that same object uphill, even if the motion is frictionless, by pushing something uphill, then we're now fighting against gravity to an extent, and then that changes our calculation. That changes, there's other things to consider there. Now, the other thing that could happen here with a constant force is if we're pushing with a constant force, pushing an object, and again, we're assuming frictionless as far as how the object moves against the ground. If we're applying a constant force but it's at an angle to the object, then that changes how that applies as well. Okay. Ultimately, we're not going to worry about the work done by a constant force. That's something that you'll get in physics, for those of you that are in physics or have already taken physics. Because that doesn't require any calculus. Because it's really just, if the work is being applied to the object in the same direction that we're wanting to move it, like parallel, then it's just a simple multiplication. But even if it's applied at an angle, then it's only trigonometry, because then you just have to take the horizontal component of the force, which is the cosine of the angle, times all that. So anyway, that's notwithstanding. What we're interested in this class is work done by a variable force. that means the force that is being applied is changing as the distance changes. Okay? And so the closer we are to a destination, the force being applied does change. And partially it may be that the weight of the object is changing, for instance. Like if we're trying to get water from a well in a bucket, and the bucket has a hole in it, then we may be pulling at a constant rate, but the weight of the object is changing as time passes, as the bucket's being raised. And so in that scenario, since the weight of the bucket changes, the actual force being applied changes. Okay, how it actually affects the bucket at that point, because now we're able to, as the weight decreases, we're able to pull that bucket up more effectively. Okay. In this case, our work is calculated as the integral from a to b of the f of x, is now our force function, and dx. Okay. So the idea here typically is that rather than have a human do this, we'll have like a machine do it that's designed to apply specific action. So we could have like a winch hooked up to this bucket as it pulls up, and as the weight of the bucket decreases, the force that is represented by is basically lower, but it's still being raised up, which requires a certain amount of work to do that. And then dx is kind of our distance from a to b. Okay, so it's still force times distance, but because the force is changing from one moment to the next as that distance changes, then it's no longer a constant force, it's now a variable force. Okay. Now, if you look in the textbook, this is on the bottom of page 485. Sorry. It talks about some of what I was discussing. They also include the CGS system, which is centimeter, gram, and second. And there we use erg as a measure of work instead of the joule, and then force is measured in dynes, and then distance is typically in centimeters. So it's really just a matter of scale. So CGS is used in smaller scale situations where we're working with centimeters and grams. Makes more sense than meters and kilograms. And then international, or what we normally call metric, would use joules, which is Newton meters, and then foot pounds, which is based on pounds for force, and then feet for distance. And we have some conversions there. Don't worry too much about the conversions. I would say whatever system the problem is presented in already, just go ahead and use that same system. If it was given us in US units or imperial units, whatever you want to call it, feet and pounds, let's just use feet and pounds. If it's given as newtons and meters, let's use metric. Okay. All right. So there's different types of work problems that we want to look at. So the first one we want to look at is lifting an object, which is kind of what I was talking about with that example with the getting water from a well, that we're just lifting up a bucket of water. Okay. So let me just give you an example. A bucket of water. Now, of course, it depends on the size of the bucket, but we know a gallon of water is, what, 8 pounds, roughly? So maybe in this bucket of water we have 2 gallons. Let's say we have a bucket of water weighing 16 pounds. And this time, we'll say the water's not leaking. So a bucket of water weighing 16 pounds is raised up to the edge, to the top of a well, that is 50 feet deep. It's pretty high up. I don't know if we have 50-foot deep wells. Anyway. How much work is done in lifting the bucket? Or how much work does this require? I guess is a better way of phrasing that. If the rope attached to the bucket also weighs 1 pound per foot. Okay. Now this is where we get our variation, because if we're just lifting up 50 feet of a bucket of water that weighs 16 pounds up 50 feet, if the rope is not involved, then we just multiply those two numbers together because it's a constant force of 50 pounds that we're raising up. Now, if we have a heavier rope, or if it's a chain, for instance, that has a little bit more weight to it, we have to also incorporate the weight of that whatever medium or object is involved here. We have to incorporate that into the calculation, because 50 feet of rope weighs not an insignificant amount. In this case, if this particular rope is pretty heavy duty and weighs 1 pound per foot, 50 feet of rope is 50 pounds. Okay? That's more than the weight of the bucket of water itself. Probably I should have added some weight for the bucket also. So maybe, so 16 pounds, maybe it's not full of water, maybe it's mostly full. Anyway, so we'll say that 16 pounds incorporates the water and the bucket, and then the rope is 1 pound per foot. So as we pull up this bucket, the less rope there is attached to the bucket. Okay? So like at the top of the well, maybe we have some kind of winch that we're turning. As the rope wraps around that winch, we no longer have to pull up that length of rope, just the amount of rope that's hanging down connected to the bucket. That's the amount of rope we're actually lifting when we turn that winch. Ideally, it's not exactly equal, but it's close enough that we can work with it that way. So in that sense, when we talk about our distance changing, of course, we're raising this bucket all the way up to the top of the well. So it's going from 0 feet all the way down at the bottom, up 50 feet to the top of the well. So we can already see that's going to be our units of integration. Okay, so we have to raise this water 50 feet from the base of the well, so 0 to 50. Now we need a force function. Okay, Now, F of x, or force, again, it has to incorporate all of the weights that are, or all the forces that are present here. So, in this case, if the bucket of water weighs 16 pounds and the rope weighs 1 pound per foot, how much does everything weigh at the very beginning of this problem? Between all of the rope and the bucket that it's attached to. So we have 50 feet of rope that weighs 1 pound per foot, and we have a 16-pound bucket of water at the end of it. So combined, our force, F of x, is going to be 66 pounds. That's how much it weighs at the beginning. Because at the initial point of this problem, the rope is completely extended and attached to the bucket. So we have 50 feet of rope at 1 pound per foot is 50 pounds, plus the 16 pounds of the bucket of water, and that equals 66 pounds total. Now, as we start to raise this bucket up, the amount of rope from the bucket to where it's being wound around this gear, or whatever you want to call it, it's decreasing. So the amount of length of rope that we have is gradually decreasing the higher up we raise the bucket. And so our force is then modified by how much rope is present. So if X is the amount of rope, then we're going to subtract 1 pound per foot of rope as we wound this up. Okay, so every foot that we raise up the bucket, it now weighs 1 pound less. And so the idea is that we start off with 66 pounds, but if we lift it 1 foot, then now it weighs 65 pounds. If we lift it 2 feet, it weighs 64 pounds. If we lift it 3 feet, we've now weighs 63 pounds. And by the time we get to the top, if we've lifted the whole thing up 50 feet, it's only 16 pounds remaining, which is just the bucket of water itself. Okay? Are there any questions on how I got this? So again, it really makes a difference what how much rope is basically applied as we lift up this bucket. So it gets easier as it goes. I mean, overall the amount of work doesn't change. The amount of effort decreases the less rope is deployed. So at 25 feet, halfway, the bucket and the rope combined only weighs 41 pounds at that point. So it's a little bit easier to lift. Overall, the work done is going to be equivalent, but more work is done in that first 25 feet than is done in the second 25 feet, because the rope and bucket weigh more at first, but less later. Hopefully this making sense. Okay, so we're just going to integrate from 0 to 50, 66 minus x. So that'll be 66x minus 1/2 x squared, or x squared over 2, whichever way we prefer to write that. And integrated from 0 to 50. We know if we plug in the 0, it's just going to zero out both of those terms. So we really only need to worry about the 50. So we get 66 times 50 minus 1/2 times 50 squared. So we get 3,300 minus, this is 1,250. And so we end up overall with 2,050. And this is foot-pounds of work. Okay. Now, any questions on this before we move on? Sorry. Okay. Well, let me create a little bit different scenario for you. Similar but different. Let's see if you can come up with the force formula. A bucket of tools weighing 50 pounds needs to be lifted up (20 feet) at a construction site. The chain that is attached to the bucket, or that is attached to the bucket, weighs 40 pounds. How much work is done in lifting up the bucket? Now, again, it's important to note that the chain starts off weighing 40 pounds, but at the end, as it wraps up around the winch that's being, used to raise it, it doesn't weigh 40 pounds the full time. So we need to figure out how much weight we have initially, and then how much is decreasing by every foot that we lift up this bucket. So what would be our formula for f of x in this case? Does anyone have that? Well, we know we have 50 pounds and 40 pounds initially, which is 90 pounds total weight to start with. But the bucket itself, or sorry, the bucket's going to stay constant. We don't have any holes in it. It's just going to be 50 pounds all the way up. But the chain starts off weighing 40 pounds. That's for 20 feet worth of chain. So that basically means it weighs 2 pounds per foot. So that's important information here. So not quite 90 minus x, it's close. If the chain weighs 2 pounds per foot, then every foot that we lift up the bucket, we decrease the weight by those 2 pounds for the chain. So that would actually make it 90 minus x. Right. So we take into account the total weight, and because it's 40 pounds for 20 feet, we know the chain is 2 pounds per foot. So every foot that we wind up the chain, we reduce the amount hanging from that by 2 pounds. Okay. What are the limits of integration here? We want to lift the object up 20 feet. So all we're really looking at when we look at limits of integration is basically a change in height. So that means we'll just integrate it from 0 to 20. So 0 is how many feet the bucket is off the ground when it starts, and we're raising it up to a height of 20 feet. And so it starts at 0, we raise it to 20, that's going to be our limits of integration. Now, this is the main part of the problem right here, is getting this thing set up. Because once we have this, these problems tend to be pretty easy to work with from there. The integration is very straightforward. I left out the x, so yeah. So 90x minus x squared. And then from 0 to 20, again, the 0 is not going to give us anything in either one of these terms, but 20 will. So 90 times 20 minus 20 squared. So it gives 1800 minus 400, which is 1400 foot-pounds. Okay. Now, when we're talking about force, if we happen to use, let's say, rather than using feet and pounds, we were using meters and kilograms. what would we have to include? Sorry. When we talk about force, if we have 20 kilograms of tools instead of 50 pounds, we had 20 kilograms, which is not far off. It's a little bit different. What other number or what other value would we need to include in our calculation? So if we let me write this down so you can understand it a little bit better. If we had 20 kilograms of tools being raised, let's say 6 meters, by a chain weighing, or that is 1 kilogram, and let's say 2 kilograms per meter. Pretty heavy duty chain. When we talk about the force function in this scenario, first of all, I worded it a little bit different because instead of giving you the total amount, and instead of giving you the total pounds of the chain, I've given you the 2 kilograms per meter. So how many kilograms does the chain weigh overall when it's fully extended to the bucket of tools? Right, so we'll have to include gravity, exactly. Whenever we talk about force, in US units we say pounds, and that already includes gravity, just because that's included in the expression. Yeah, but whenever we work on metric, we have to make sure we include that 9.8 or 9.81, to be a little bit more exact, as our gravity as it applies to our object. So we have 12 total kilograms of chain plus the 20, so we start off with 32 kilograms, and that is being decreased by 2 kilograms every meter. But again, that's also affected by gravity. So we'll do 9.8, just for simplicity's sake, times 32 minus 2x. So when we look at this in metric rather than imperial units, that's the difference that we have to incorporate, is we have to incorporate gravity as part of our force calculation, whereas when we talk about pounds, it already includes gravity in it. And that's just the biggest difference between imperial and metric right there. Anyway, so the weight of an object, the pounds, is not a force measure. It's actually the force. Well, it's actually gravity is already included. So here we want to make sure we do mass times gravity. So this is the mass measure of the objects, and this is the gravity. Okay. So if we're given the expression, or if we're given the problem in metric, we do alter it a little bit based on that. Or, well, we just want to make sure we include the gravity calculation as well. Although, in general, I'll probably give that problem to you using US units, just to make it a little bit easier. All right. continue. The next work problem we want to look at is the work done in stretching or compressing a spring. Okay. Now, our general formula for work is still identical. Work is still the integral of f of x dx from a to b. But, I mean, that's always our formula for work done by a variable force. The one thing that changes from one type of problem to the next is how we actually get that force formula. Now, when we're talking about a spring, does anyone remember the law that kind of governs the physics of springs? Hooke's law, yes. And so Hooke's law says that the force exerted by a spring is equivalent to K, which is called the spring constant, times X. Now, this is the what we call the restorative force of the spring, because the tendency of a spring, whether it's stretched or it's compressed, the tendency is for the spring to want to return to how long it normally is. So if a spring is normally this long and we've got it compressed, this is the force at which it wants to push out to return to its original length. And so even if it's stretched or if it's compressed initially, it's still trying to return to its natural length of the spring. Again, because everything tends towards equilibrium, basically. And so K, in this case, is what we call the spring constant. And the spring constant is basically a measure of how strong that spring actually is. So if we have a more heavy-duty spring, like the ones that we have in our garages to open the garage door, those are pretty heavy-duty. They're pretty good spring constant. Versus a slinky, which has a pretty low spring constant, because those don't want to restore too well because you can keep them stretched pretty easy. Okay, and then X is then the displacement from its original position. I don't know if y'all can hear my computer right now. It's developed an issue. I just might have to clean the fans or something. It's kind of annoying to me. I don't know if it's annoying y'all. I hope it's not too bad for y'all. Okay, now X being the displacement from its original length, this is an important comment, or an important aspect of this problem, because when we measure X, we measure distances when we talk about springs. It's always relative to the original length of the spring, or what we call its natural length, or whatever length it's trying to restore itself to. So let's say, for example, a spring has a natural length of, let's say, 10 centimeters. A 20 Newton force applied will stretch the spring to 15 centimeters. How much work is done in that process? Okay, so first thing we want to do is recognize that the natural length of the spring is 10 centimeters. So 10 centimeters is basically x equals 0. Okay, the natural length is basically the 0 position. So in that sense, what value of x represents 15 centimeters? How far are we displaced from its original length? So if it starts off as 10 centimeters and is stretched to 15 centimeters, then the difference there is it's been stretched by 5 centimeters. So x is equal to 5 in that scenario. Basically, if 10 centimeters, the natural length is corresponding to x equals 0, then by stretching it to 15 centimeters, we're now 5 centimeters away from where we started. So the main thing with working with springs is that all the distances or all the measurements are relative to this original position, this original length. Okay. So we have x equals 0 to x equals 5. So that's going to be our limits of integration, and because we know a 20 Newton force stretches the spring by 5 centimeters, this will allow us to find the spring constant K for this particular spring. So if we use F equals Kx, 20 Newton force, and 5 centimeter displacement, that means that K is going to equal 4 in this case. And that's newtons per centimeter in this instance. Okay. So f of x equals 4x based on that. Okay. So that's our variable force formula. And so the work done then is equal to the integral from 0 to 5 of 4x dx. So we take our information. First of all, we figure out what the x values are for each of the values in the problem. So in this case, 10 centimeters is x equals 0, 15 centimeters, x equals 5. And then we know a 20 Newton force will stretch the spring by 5 centimeters. So we plug that into Hooke's law, F equals kx, which says that 20 equals k times 5, so k must be 4. That tells us the spring constant. This is how strong the spring is and its relative strength in trying to restore to its normal position, normal length. And so knowing that k is 4, that means our function f is actually 4x. We leave the x now, and then we integrate from 0 to 5. And that gives us a value of 50 Newton centimeters as the work being done. Okay. Let's work another spring problem. Let's see. Well, this time we'll have a spring that has natural length of 20 centimeters. And now we'll say a 20 Newton force compresses it to a length of 18 centimeters. How much work is done in compressing the spring from 15 centimeters to 10 centimeters. Okay. Now again, 20 centimeters, that's the natural length, that's x equals 0. 18 centimeters means that's x equals 2. 15 centimeters, x equals 5. And 10 centimeters is x equals 10. Okay? And again, notice that from 20 centimeters, if we compress it to 18 centimeters, that's a difference of 2. If we go from 20 to 15, that's a difference of 5. And from 20 to 10, that's a difference of 10. Now, notice that in both problems, whether we were stretching or compressing the spring, we used positive values for our x's. It actually doesn't matter if we use positive or negative, but we can use positive as long as we're only going in one direction. Now, the only time we would need to use negatives and positives in the same problem is if the spring was going from a compressed state to a stretched state or vice versa. Then the signs would be important. But as long as we're going from compressed to compressed or stretched to stretched or natural to either one, then we don't need to worry about the signs. We just keep using positive numbers for everything. So 20 centimeters corresponds to x equals 0. If we compress it by 2 centimeters, we'll say, okay, that's x equals 2. If we compress that by 5 centimeters, that's x equals 5. And if we compress that by 10 centimeters, then that's x equals 10. So basically that's how different we are from its original length. That's our x value. Now a 20 Newton force compresses it to 18 centimeters. So this statement right here, this allows us to find K. Okay. What is K in this case? What is our K value? Does anyone have the K value? So we took a 20 Newton force and we compressed it to 18 centimeters, which is a difference of 2 centimeters. So we'll use x equals 2. And solving for K, we divide the 2 over, so 10 is equal to K. So K is equal to 10, so F is equal to 10x. That's our force formula in this case. So we'll plug 10x into our integral. The other thing that we need to focus on is what are the limits of integration? Well, we know we're trying to find how much work is done in compressing the spring from 15 centimeters down to 10 centimeters. And so for our limits of integration, we again look at our modified x values, which is how, the displacement. So we're going from 5 centimeters below natural length to 10 centimeters below natural length. So we'll integrate from 5 to 10. Okay. So we do our integration. So it's 5x squared from 5 to 10. So we end up with 5 times, what is it, 75? Was that 375? 350, 25, 370. Yeah. Now again, this is in Newton centimeters. So we can make that 3.75 Newton meters or 3.75 joules. Okay. So in these problems with the springs, typically we'll have a statement such as this that allows us to figure out what the K value is, and then they tell us how much they want us to find how much work is done by going from here to here, and you have to look at those values and compare them to the original value to get the displacements, the x values. And so that tells us how far we have to compress or stretch the spring by, and then how much work is done based on that. All right. Don't think we have enough time to talk about emptying tanks of water, just or other fluids now. Let's see. So for homework, go ahead and look on page 491. Look at number 9. $11. 13. And then 29. $31 and $32. Okay. The first 3 problems are on springs, and then the second 3 problems are on lifting an object with a variable weight chain. So, all right. So you all look over those, and we will continue from there on Thursday. Y'all have a good rest of the day, and I will talk to you then. Take care.